So now I'll give you guys one further improvement upon k nearest neighbor. So now suppose you have, when you look at the data, and I'll slightly exaggerate, let me take this mouse from here. Oh yeah, I have my hand actually. This is touch sensitive, so I should just be able to use my finger. Awesome. I keep forgetting that. And then I should disable touch for the time being. See, suppose you're trying to, let's look at this function. So suppose the underlying reality is complex. So I'll just draw the reality and draw the points. Something like this, right? This is the underlying reality, yellow line, but you can't see that. What you can actually see are the data points. Right. Something like this, huh? Now I ask you this question. Tell me the value. Tell me the value at a point that I haven't seen, which is, actually, let me, just for the sake of argument, remove these 2 points. I ask you, at this value of x, let me just mark it as x naught, sorry, x naught or x tilde, just to imply x tilde, what is y? Predict y. So what will happen is, suppose I asked you to look at 3 nearest neighbor. I'll take an example. So what will happen is, you will take, hopefully, you will take these 3 examples, and your prediction would be, what would your prediction be? Your prediction would be the average of these 3, which would be, this is your y hat. But what is y? Y is, this is the actual y, isn't it? So you had a gap, you had an error here, y minus y hat. So you ask yourself, is there a way that you can fix this? Can you think of a way to fix this? What if you listen to the nearest neighbor more than you listen to the next nearest neighbor, and a little bit less to the one a little far off?
Like you do in time series forecast.
Not time series. Yeah, hold those arguments. See, this is new. You're in new territory. Don't do similarity. But in time series, yes, same thing happens. More weightage to the nearest one than the. But don't bring that, because at this moment, just look at it in its pure form. Actually, time series gets its intuition from here, not the other way around, right? So suppose you are here. Would you agree with that, right? Right? If it rained yesterday, that's a stronger predictor of raining today than the fact that it rained 1 week ago. Yeah. So yeah, sort of in a way, Bayesian conditioning. But this is it. So in other words, let's believe what you do is you take the k points and sort them, sort by distance. Let's call the nearest point x1, second nearest point x2, and third nearest point x3, x3, sorted by distance. And now you compute the distance to all of them, d1, d2, d3. So you computed the distance to the 3 points. And now what you do is you want to take a weighted average. You want to somehow not see, initially, what were you doing? You were doing y, and associated with each of them is a y1, y2, y3. This is fact, right? This is your data, right? X1, y1 are the data points. What you do is, initially what you were going to do, just KNN, you would do y hat is equal to 1/3 y1 plus y2 plus y3. Just average it, isn't it? But we are saying that don't do that. Somehow and this method is called a kernel KNN for a reason that you'll see shortly. Make your y hat somehow a weighted average. So let's say y1 times some multiplying factor. Let's say some kernel k1 plus y2 k2 plus y3 k3. All right. So for example, those could be multiply this by 3, this by 2, this by 1. Do you get the intuition, the nearest neighbor multiplied by more or something like that? Does it agree with your intuition, guys? Right. The only question therefore that remains is, what is this kernel? You realize that kernel, this k are called kernels. Kernels. Now, when we talk of kernels, don't take a computer science meaning of kernel. In computer science, the moment you say kernel, it means you think operating system and the core of the operating system, right? No, this is a mathematical kernel. And kernel word keeps popping up in this space quite a lot, actually. And we are getting into this territory now. So kernel is, let me define it. Distance, specifically, it's a distance kernel. Now let's define what a distance kernel is. Distance kernel is a monotonic continuous function of distance. Monotonically decreasing function. What does monotonic mean? Means as distance increases, there is no chance the function will climb up, right? So suppose I plot distance. You know that distance can only be positive. Is of course greater than equal to 0. Distance is there. Now, for every value of distance, kd, it can only decrease. So what can be a decreasing? It cannot increase. It has to decrease. So all of these are valid. I can just say, what about this straight line? It is decreasing. Is it monotonically? Like this is valid. But what is not valid is if I had said, why is this not valid? Because it starts increasing, right? So monotonically decreasing, and this is valid.
The decay function also, right?
Yes, and we're coming to anything. Yes, all of those. And so let me turn this off. So what happens is that this is okay. Then another thing I could do a step function. Is this okay? Is this monotonically decreasing? Well, it stays flat and then it falls. This also is okay, right? I could do, like you pointed out, Gaussian decay function. That too is fine, right? I could use cosine decays, right? Cosine curve falls down, cosine wave. That also could have been there. This is fine. Anything that is monotonically decreasing will suffice. So long as it decreases with distance and at d is equal to infinity, it goes to 0. Are we together? And therefore, now what happens? Your y hat, therefore, is just this x1, the sum of these, right? So in other words, it is x1 kernel 1 plus x2 k2 plus x3 k3 with, of course, the normalizing constant. You have to normalize it down to 1, right? Otherwise, it won't make sense. So for example, you remember we did divided by 3. When all the k's are 1, you have to divide by 3, right? So k1 plus k2 plus k3 and so forth, right? You do that and you get a weighted, weighted average. What we are looking for is a very simple concept, weighted average, isn't it? And so you get a weighted average. Any questions, guys? So this idea, and I introduce you to the very interesting word today, kernels. Kernels are everywhere in machine learning, right? We'll encounter them a lot. And in fact, the next week, we will start with a new class of algorithms called support vector machines. They are all kernel machines. And I thought today would be a good segue by first introducing you to some notion of it.
So this norm thing, isn't this pretty hard to do? I mean, like figuring out what component of the, say for instance, that you had 3 neighbors.
Yeah.
2 of them were right at the extreme and 1 was over here. Then this guy would predominantly make
the nearest neighbor would have a dominant effect.
Right?
Yeah.
But if you had like say 3 of them very close to each other, then that then what would be the, then it's 1/3, 1/3, or like
no. So see, here's the thing. Suppose your data points are like this: 1, 2, 3, 4, and you're trying to make a prediction at this point.
Good.
Right? So what will happen is that this will get a heavy weight.
Yeah.
These will get lesser weight. But ultimately, there's a denominator that balances it out, that sort of scales it down. And so what will happen is the whatever value is here, right? The real value, predicted value will be, and let's say that these guys are predicting values here and here, right? This. So what will happen is, because you're taking the weighted, you're more likely to be slightly less than the nearest neighbor. Right. Which is what you want. Which is what you want
to come closer to the nearest.
Yeah. In other words, nearest neighbor should have a louder voice. Yes. It's a simpler way of putting it. Let me write it down. Nearest neighbor should have the biggest say. Vote say in the prediction. So this is the question of kernel nearest neighbor. So now here's some suggestion, guys. You realize that kernel is a common sense thing, right? Whenever you do nearest neighbor thing, it's always a good idea to use a kernel. I would say that by default, you should use a kernel. Right? To not use a kernel is also a kernel. So for example, let us take this line, which remains flat. A flat kernel is the ordinary KNN, isn't it? Irrespective of how far you are, the weightage is the same. But other kernels improve upon it. So generally, and the reason I mention it, for example, in the textbook, KNN is there, but kernel KNN is not emphasized. Sometimes you get pretty good improvement simply by using kernel KNN rather than KNN. And you see the intuition why. It speaks to common sense that it will often work better. Right? So use kernel KNN. Next week, we'll do some notebooks using kernel KNN, and you'll see what it means.
So what you're saying in some words is like a microscope, you need to look at all the small neighbors and see how the values are kind of gradually smoothing out, or what's the trend in the
what is really happening,
and write like a function which can mimic that.
Exactly. Zero in there and then make a local prediction. Local prediction. Now, related to it, now comes an interesting thought. Okay, so there are 2 thoughts that I want to do. I'll park one idea which I shouldn't forget. Kernel plus linear regression is an idea. I'll park it for a moment. Now let's go back and ask this question. So what is K? What are good kernel functions? So it turns out when this idea came out many years ago, actually, lots of people began to create their own special kernel. They all had the quality that they would decay. And then they'd say, this is better than this, and this is better than that, so on and so forth. So and obviously we'll do it in the next lab. You'll see that I'll come out with many kernel functions. The Gaussian kernel, decaying, the whatever, I mean, the linear kernel, the sine wave kernel, so on and so forth. There are many such kernels and they all have fancy names. After a few more years of cooking up kernels, people realize that actually it doesn't really matter which kernel you pick, so long as you pick a sensible kernel. The answers are very close to each other. Right? It matters a little bit if you're super optimizing, yes, find the best kernel, but generally, so long as you choose a sensible kernel, you will get an improvement, right? And we'll do the lab with it the next time. Next comes a very interesting thought. And this is a thought that is lovely, actually. So let's look at this data point. Once again, where is our data point? Blue we use for data points, right? I keep forgetting what color we use for data points. Suppose you do this. You ask a slightly different question. And so you can imagine that this will go back. This is your data set 3. No, data set 2, right? Data set 2, sorry. Yes. What if I told you that suppose you take a certain number of points, you take a neighborhood, again, think of your epsilon neighborhood kind of a thing, right? You find k nearest neighbors, but instead of taking the average of them, you realize that this reality I can use to make a locally linear model, because what they are predicting here locally is this, right? This, all of them are predicting different lines, isn't it? Locally, this is the line, and that line is a pretty good prediction line for points in that neighborhood, isn't it? Or another way to put it is that smooth curves have tangents. Those tangents are pretty good reflections of what's happening locally. And so those tangent lines are linear models. So what you could take is a few neighbors and just build a linear model. Are we together? So that is where you put your neighbors together and you build a linear model. And then you can go even further. You can say, when I build the linear model, I'm going to give differential weightage to the errors, the loss function, the errors. I'll put more weightage to errors made in predicting the neighboring values versus predicting the far off values, right? You can keep on doing many optimizations like that. And so when you put KNN and together with linear regression models and put the two together, you again have a fertile ground for many ideas. And so, I'm just giving you a sense of the classical in the tradition of machine regression, how many things people have tried.
Is this what we call as piecewise linear regression?
This is, well, piecewise linear regression is, yeah, this is very close to it, pretty much it. But except that here, the piece sizes are not by discrete, you're not breaking the x-axis in discrete sizes, but you're picking it by the number of points. But amounts to almost the same. You can think of it as, it is piecewise in nature, but by k, by number of neighbors. Whereas you could do it discrete by fixed size segments along the x-axis, right? Things like that. So there are many variations, and you can sit down and cook up more variations.
So this is good for the missing value imputation, like if you wanted to. Yes,
missing value imputation and so forth. K nearest neighbor is often used for that. So guys, this is about K nearest neighbor. How much energy do you have to learn about yet another new topic? Or should we skip it for today?
This particular small line KNN.
Yeah.
Is it same as when the kernel is absolutely linear?
No. It has not to do with that. No. See, Abhishek, no, you're getting it wrong. See, here I'm taking this. Forget about kernel altogether. Just simple KNN. 5, I'll take 10 points near that point. Wherever I want to make the prediction, I will take 10 nearest neighbors. And I'll build a linear regression model out of those 10 points.
It's like fitting a straight line.
It's fitting a straight line. It will be just a tangent line, right? Tangent line going through.
That kernel is just degree 1.
Kernel is just a straight line. K is equal to degree. Kernel is effectively a straight flat kernel.
So it will be the same.
No, that straight kernel has nothing to do with the tangent that you drew. No? The locally linear model you drew. You're mixing the two up. So here's the thing: take the KNN and forget the kernel part altogether. And now, so let me repeat it. What you do, Abhishek, is, so here's the thing. Suppose these are the points. I'll take points like this. These are your neighborhood points. Now, observe these neighborhood points, how they are. They are like this. If I were to build a simple linear model, I just gave you these many data points. These are your K nearest neighbors, K and N, K nearest neighbors, right? I just picked the K nearest neighbors. I'm putting it here and I'm saying, okay, draw me a regression line through these.
Okay.
What is the regression line you would draw?
This part is okay. And then based on that line, we will predict the model.
That's right.
Now, if we say that from that point, what is the distance of these points? And give the weightage as per the.
You could also do that, yes. Like while training the linear regression. No. So be with me. See, you could entirely forget about kernel and just draw a straight line through the data, right? Then there are adapted versions of it, which says, hey, you know what? The errors that you have when you're writing the loss function and training the model, you could introduce a kernel on the error, saying that neighboring points predictions getting wrong is much worse than further point predictions getting wrong. Right, so it will fit more aligned to the nearest points and there. So then the kernel would come in, and you could use any one of the smoothing kernels. That's that. That's that. That is it. Okay. So guys, so you
have to remember this for next time's lecture for the SP, and that's why you did it now. I
just taught you a baby. Distance kernels are basic.
That and this.
Yeah.
Is like the jumping.
It's a segue into that. It's a segue, but it's a very basic. Distance kernels are the simplest sort of kernels. When we go into support vector machines, actually, you know what? Okay, here's the choice, guys. We took a respite. I hope you found that clustering was a lot easier, except for Denclu, where I brought in the field. There was not much mathematics here, right? So it was a respite from mathematics. We have two big topics to cover. Today is the 8th lecture, isn't it? So we have 4 more lectures. We have ensemble methods like random forest, gradient boosting, which will be more or less mathematics free. And we have kernel methods, support vector machines and so forth, which are heavy in mathematics. So not very heavy, but heavy enough. So which one would you like to do first?
Support vectors.
Support vector machines. Okay. It ties up with that. It does. It's a good segue into that, right? But that kernel is slightly different and more complicated, but it is it, right? So we'll do support vector machines next week.